Now let us move on to elementary signals. So what we will do here is we will look at again some of these basic signals that you have already seen in signals and systems. So this will be review if you have already seen them, and then we will again point out similarities and differences just to reinforce these points just in case we have not paid attention to them. So we will start off with the unit step sequence and then the unit impulse and then the sinusoids. The discrete time impulse is the most elementary of all signals, is the simplest discrete time signal you can think of. But since what we are going to do now is we are going to compare each elementary signal with its continuous time counterpart. The discrete time sequence is the simplest one, but its continuous time counterpart is really complicated. We will come to that after we introduce the unit step sequence. So the first thing that we want to look at is the unit step, and this analogous to the continuous time case, this is defined as 1 for n greater than or equal to 0 and 0 for n less than 0. And the picture that is associated with this simple function is this: solve ones for n greater than or equal to 0 and 0 for n less than 0. And again, just to make a note of this in case you are not already noticed it, n less than 0 is the same as n less than or equal to minus 1. So this is the discrete time unit step sequence. The corresponding continuous time unit step function is 1 for t greater than 0 and 0 for t less than 0, and the picture associated with this is it is 0 for t less than 0 and 1 for t greater than 0. But you must have perhaps encountered some slightly different definitions. For example, u of t could be 1 for t greater than or equal to 0 and 0 for t less than 0. So let me call this as u1 of t. All right. So this is a different definition, and once you have seen this variation, you can also guess some of the other variations. So u2 of t could be 1 for t greater than 0 and 0 for t less than or equal to 0. So one more variant, can you suggest? Very good. T greater than 0 it is 1, for t less than 0 it is 0, and that for t equal to 0 it is half. then as I always like to say, here is my definition of u of t, which you will not find in any book. So, this is 1 for t greater than 0, 0 for t less than 0, and at t equal to 0, it happens to be my lucky number 13, all right. All right, we will come to this in a minute. So, let us focus on the CTFT of u of t, all right. So, let me call the CTFT as u of omega, and then if you recall your continuous time Fourier transform, u of omega is 1 by j omega plus pi delta of omega. Okay. So, now we have various definitions of u of t, and this is the transform of u of t, which begs the question of which u of t. Okay, you say this is the transform of u1 of t. Okay, why is it that? So, okay, let us defer on whether that is the right answer or not. If you say this is the transform of u1 of t, then what is the transform of u2 of t? Somebody said same. Okay, it's very good. 1 point won't matter, very good. All right. So, all these things have exactly the same Fourier transform, very good. Suppose I take u of omega, which is this, and then I take the inverse Fourier transform, right. I should get back u of t. Which u of t will I get back? u1 of t, okay, your favorite unit step function. All right, so let us now, yeah, go ahead. All right, so 1 for t greater than 0 and 0 for t less than 0, all right. If you look at the inversion integral, it is defined for all t, correct? So, why do you want to leave out t equal to 0 and leave it undefined? All right. So, what is happening here is, in terms of the Fourier transform, the answer that was said saying all these various definitions of u of t will still give rise to exactly this Fourier transform, that is right, because one point is not going to contribute to the integral. If you now take this Fourier transform and then if you do the inverse transform, remember, if you recall what is happening in Fourier series, at a point of discontinuity in the signal, to what value will the Fourier series converge to? To the average value, right. So, this is no different from what is going to happen with the Fourier transform, alright. So, when you take the inverse Fourier transform of this, because t equal to 0 is a point of discontinuity, what you will get as the inverse Fourier transform of this is u3 of t, okay. So, this kind of adds some more completion to your understanding of the unit step function in the continuous time domain, even though you have seen this in your earlier course. These are some questions, I do not know if they occurred to you to ask. These are the kinds of questions that you should be asking when you look at these things. See, these are not complicated questions, they are very simple minded, and yet when some of these questions were raised, even though you had seen them before, they were not full or complete understanding. So, whenever you look at something, try to ask these very simple minded questions and make sure you understand things as fully as you can. So, that is the reason why I brought up u of t, even though you had studied unit step function in your earlier course and also its transform. So, these are some of the similarities and differences that can occur between continuous time and discrete time case. As far as u of t is concerned, at t equal to 0, there are various definitions possible, whereas in the discrete time case there is no ambiguity in the definition at n equal to 0.